Our next speaker is Zach, and yeah, you're going to tell us about our numbers and all the work you can do there, or some of the work.
Brilliant. Yes. Thanks, Jack. Thanks for having me. Yes. So a few things to say before I begin. In the title that Jack asked for in the email, I said this is about estimating reproduction numbers with no SIR equations. So if you're not an epidemiologist and you've forgotten how SIR models work, or if you are an epidemiologist and you're sick of SIR models, then that's good. The other thing is, I did a talk yesterday, and so I've tried my best not to repeat myself too much, but at the beginning of the talk, I will repeat myself a little bit. And don't worry, it's not 40, because I skipped through a fair bit. So a little bit about reproduction numbers. Reproduction numbers are used in a variety of different fields. Perhaps the most, so for example, population dynamics, but perhaps the most popular one is epidemiology. So some background. So yesterday I talked about the case reproductive number, and I think this is the most intuitive type of reproduction number. The average number of people someone infected at time t can expect to infect. So there's about maybe 15 of us in the room here at the moment. Over the course of all our infectious periods, infected 45 people, then the case reproduction number for us would be 3. And I think that's a fairly intuitive understanding of it. The instantaneous reproduction number is, I think, a little bit harder to understand. It's the average number of secondary cases that would arise from a primary case infected at time t if conditions remain the same after time t. And the reason you have that if there is because you're not able to see infections in the future, and so the way you're estimating the reproduction number is to look at all the infectious potential today, look at how many infections there were, and then from that estimate the reproduction number. The other thing is the generation interval. So this is the time between infection events in a transmission chain. So if I'm infected today or get infected today and I infect you tomorrow, then the generation interval is 1 day. And like I said, we're going to be focusing in this talk on the instantaneous reproduction number. The other thing to say is that all these definitions have an analogy or an analogous definition, well, particularly the generation interval. So you can just switch infection events with when someone displays symptoms. And in general, you know when someone displays symptoms, you don't know when they're infected. So the serial interval is more commonly used. And the notation I use is for this generation interval distribution is WI. So the probability that the delay between infections is 1 day would be W1. Okay, so I showed this as well yesterday. So I simulated this epidemic using something called the renewal equation, which I'm going to explain a bit more in detail in the next slides. So to do it, you take the generation interval, and then you take the known reproduction number that you invent, and then you can generate incidence on day 1. Well, no, you take some incidence on day 1, then you can generate incidence on day 2, and then using incidence on day 1 and day 2, you can generate incidence on day 3, etc. And then this was just comparing these two definitions of the reproduction number. So the black line is what I've used to simulate. On average, we expect that the number of people who displayed symptoms on day 12, is it 12? It's probably more like 15. On day 15, how many people did they go on to infect? Well, on average, it was about 1. That lines up roughly 1 on the y-axis. And you can see the interesting thing about that is that the red curve drops down beforehand. It looks like it's predicting the future, but actually it's because it's seeing all the data. So there's nothing special going on. The blue curve, though, is tracking the black line, which is what we want to do, and which is what we want to see. And even though it's bouncing around a bit, it's doing a reasonably good job. There are ways to smooth this, so you can if you have a kind of smoothing window, you have to introduce an assumption that the R number is constant over some window, and then you can get a smoother approximation. And that's typically what people do, given sort of weekend effects and stuff that you see in data. I'm going to talk about not including a smoothing window today. So the idea really is this equation in the top right. So IT given RT is a Poisson random variable with this rate parameter. And that's what I want to commit to of. So I've lined up, this is what a serial interval might look like for the distribution. And I've lined this up. You'll see why I've lined it up like this in a moment. So the x-axis is going opposite. But this is the probability that the serial interval was 1 week, and then 2 weeks, etc. So the thing about it is how many infections will people displaying symptoms on week 3 generate on week 4? And I think the way to think about it is over the course of their entire infectious period, if the reproduction number at week 4 was the same, you'd expect it to be I3 times R4. That's how many infections you'd expect there to be in total, if the reproduction number remained the same. But then the proportion that you'd expect 1 day later, you just multiply that by W1. And then the same for how many from week 2 on to week 4, and etc. And so then the expectation of I4 given R4 is just the sum of all those things. I wrote this bit a while ago. I'm not even sure what FRIC means. I think what I was saying is if you take the sort of assumptions from a Poisson random variable, which I've forgotten what they all are, but they're all there, then you can say IT given RT. Let's say it's a Poisson random variable with the expectation as the rate parameter. Okay, how are we doing for time? So you might be familiar with EpiStim. More people than I expect have heard of EpiStim. But this is basically the renewal equation on the previous slide, and it uses conjugate priors to estimate the reproductive number, instantaneous reproduction number. So we want to use Bayes' rule. So we want to get a posterior for RT given the data on day T. And I'm really just showing you conjugate priors. So the key is letting RT be a gamma random variable with shape and scale parameters A and B. Then the prior is proportional to this thing. Just showed in the previous slide that if IT given RT is Poisson, then that likelihood is proportional to this. You can tell, multiply them, you're just going to get a gamma posterior. And you make a small edit to this when you look at smoothing windows, assuming that RT is constant. Also quite a problem that my supervisor and I have been trying to solve. The renewal equation that we've just talked about, it can't account for infector-infected pairs coinciding within the same calendar time step. So just to look at that equation again, just in the top right, it's saying that IT, cases arising on day T, will arise due to cases prior to day T, not including day T, or week T, or month T, or whatever time interval you choose. And that could be because there's no reason why, if I'm infected today, that I can't also infect you today. And particularly if you've got a fast generation time, that could be a problem. Typically, though, where this issue arises is if you've got a pathogen like influenza, then the generation time is like 2 or 3 days. I can't remember off the top of my head, but something like that. And if you're given incidence data over weeks, then you can't account for within week transmissions, and so you're going to get your RT inference to be messed up. Just to explain that maybe a bit more. Say you've got, this is the actual transmission tree, time's going this way, and then you've got the nodes are in infections. Then if Bob and Claire displace instance on the same day, even though Bob infects Claire, then you're going to have an issue because the incidence is just going to show 1, 2, 0, 1. And so you're going to say the incidence on day 2, which was 2, you're going to attribute that they're infected to being on day 1. But the reality is that the Claire was infected by Bob. So that's the issue in a nutshell. I'm now going to skip through loads of slides because initially when we're trying to solve this problem, basically having the renewable only thinks about one generation, but you could think about multiple generations. So we had a way of trying to do it with multiple generations, but then we decided the best approach. So I'm going to skip this. What we've decided to do instead is about partitioning the incidence data. So I've added in these red lines, and if you add in the red 1, 1, 0, 0, 1, 0. And so now we've got a case where where C could plausibly be infected by B, and that's what we want. So I'm a bit worried about these schematics that it's going to not be very good, but because there's a lot going on. But the idea, just from this slide, is that we try to discretize our serial interval into something more appropriate. So you have to do a discretization step, and you choose a discretization that's more appropriate. And then you assume an R number, and then you use your serial interval, and then you generate incidence with that R number. And if that partitioned incidence, so these orange bars are thinner than the blue bars because they've been split. If the incidence on week 1, then we accept that value of the R number. So it's basically approximate Bayesian computation. Hopefully you can still see this. So, then the question is, do we get more accurate RT estimates or not? So this again is a synthetic data that we've used. And what's it showing? The black line is the true R number that we know, or pretend we don't know. And then this is how and the blue bars are the incidence over weeks. I mean, this is like an extreme example of becoming really badly discretized. So if you just did 1 week with this serial interval, I recognize I'm not plotted the continuous version, but you would basically get, it can only happen on week 1. So we're using a bit of a silly example, but just to emphasize. Whereas if you partition discretize your serial interval into days, then it looks like something a bit more sensible. And so these are the results. So just looking at p equals 7 versus epi-estim, just doing what you would normally do, you can see that the orange line, which is part of our method, is closest to the black line, which is what we want. And then this relative error is just, yeah, I'm not sure why I put that up. It's just interesting. And results, so this is just sort of repeating this over for 100 simulations or something, and then varying p. So you can see that there's a pretty big drop just from changing p equals 1 to p equals 2, and then you can see it flatlines, and then you can't really get below a certain error. And yeah, so one of the interesting things about this is that I think you can actually predict which p-value is going to be optimum. So because we're using ABC, the computation is going to get sort of linear. The time for the computation is going to be increased linearly as you increase p. So you don't want to be using like a massive value of p just so you're sure. You want to be doing some kind of calculation beforehand to work out the best p value. Feeling the presentation ends very abruptly without a thank you slide. There's more results. Sorry. This is real world data. This is like illnesses in Wales, and you get a similar thing. Although yes. So here our error against sort of p is a very large number because we don't know the true R number. There was a thank you slide. But yeah, that was it. Thanks for listening, and any questions?